Okay, chemistry. Hey, I'm going to go through how to use solubility rules to determine what precipitates in a double replacement reaction. I've got a video queued up here from a website called beautifulchemistry.net. This group just photographs or videotapes different chemical reactions happening, and it's pretty. They just kind of go for the artistic side of the chemistry, and it's just kind of fun to watch. But here is a precipitation reaction. So this is two solutions, okay? The black background, it's actually just a clear solution of probably sodium chloride, so table salt. And there's drops of silver nitrate, AgNO3, being added to this solution of sodium chloride. And what happens is this white precipitate forms. Okay, so they've given you the chemical reaction. They even showed you in bold what the precipitate is. So this is silver chloride, the white stuff that you see. And then left in solution that's dissolved and not visible to our eye is sodium nitrate. So sodium nitrate is soluble in water, so we don't see it as a precipitate. Okay, so I've gone ahead and written this a little differently, just using our notation with AQ meaning dissolved in water and S meaning precipitate. And I just want to give you a little overview of what's going on with the ions here. So in solution, silver nitrate dissolves into its cations, and anions. So I've kind of just mixed up some silver plus and some nitrate NO3 minus. Okay, notice that they're in a 1-to-1 ratio because their charge are +1 and a -1. So I have 2 of each in there. And then sodium chloride is also a +1 and a -1. So when those get put in water, they dissolve and separate, okay, into their ions. Okay, and then I add this solution into the other, and I get a solid at the bottom. That solid is AgCl, and I'll try and balance this just to show you everything that's happening. I'd have all that AgCl solid kind of falling to the bottom of the beaker. You know, it starts out cloudy, but eventually it'll settle at the bottom. And then left over in solution, I've got some sodium ions, and I still have some nitrate ions. Now, I only, wrote 2 of each, but there's trillions or quadrillions, or actually we'll end up talking about moles. We have many moles of this chemical, so many individual ions floating around of sodium and nitrate left over, and all the silver chloride ended up in that solid form. Okay, so this is what's known as a precipitation reaction. Okay, now without seeing the video, you'd wonder, well, how do you know that the silver chloride is what's forming the precipitate? How do I know that that's the solid and not the sodium nitrate? And so to know that, you'd have to use what's called solubility rules. And solubility rules are basically a set of guidelines that chemists have kind of observed and summarized in a little table that kind of makes it easy to identify what will dissolve and what won't dissolve in water. So these can be found just by doing a little Google search. You can find solubility rules. I'm just gonna get a little table of them. I'll post this up so that you guys have it. On Canvas. But let me copy this picture. I think I also had it already in here, but put it in again. Oops. Sorry, if I can move it around, make it bigger. So most chemistry textbooks, and I know you guys don't have one, but most chemistry textbooks have this table when we talk about chemical reactions and solutions, and they all look pretty similar. So what this is a list of different ions, and when they form compounds, whether they're soluble compounds or insoluble compounds. So the soluble compounds are listed at the top. Okay, so things that contain lithium, sodium, potassium, rubidium, or any alkali metal which is the group 1 metals, and the ammonium ion are always soluble. There are no insoluble exceptions. So anything that can partner with sodium, lithium, potassium, rubidium, cesium, and ammonium, like say for example sodium chloride or sodium nitrate, or maybe we have potassium chloride or potassium sulfate, or anything containing one of these metals or the ammonium ion are soluble, and there's no insoluble exceptions. Anything containing nitrates, bicarbonates, and chlorates are also always soluble with no exceptions. Okay? Things that contain chloride, bromide, or iodide, okay, they are generally soluble, but if they contain silver, mercury, or lead, then they would be insoluble. So in this case, like say we had a chloride, let's give it iron chloride, FeCl3. That's iron 3 chloride. Well, that would be soluble. But if I had, say, PbCl2, that's lead 2 chloride, this would be insoluble. And what that is, that's following this rule, because I have chlorides which are generally soluble except if they contain lead, mercury, or silver, which makes lead chloride insoluble. Okay, but since iron isn't on that exception list, then iron chloride would be soluble in water. So iron chloride, because it's soluble, when it's written in water, I write as AQ. But because lead chloride is insoluble, it would form a precipitate or stay in the solid form when you put it in water. Okay, so the compounds at the bottom of this table, excuse me, are generally insoluble. So carbonates, phosphates, chromates, and sulfides are insoluble except when they contain alkali metals. Okay, so like say for example I have sodium carbonate. Well, I look and I'm like, oh, carbonates are generally insoluble. However, in this case, it's partnered with sodium, which is an alkali metal. So that's a soluble exception, so I would write AQ. Okay, but if I had a different carbonate, let's go back to iron. So let's see, Fe2CO3, 3. So that's iron 3 carbonate. Okay, iron 3 carbonate. Because carbonate's on the list of insoluble, and because iron is definitely not an alkali metal, iron is a transition metal. Okay, in this case, this would be a solid in water. It wouldn't dissolve. So a way to say insoluble is to write the S, which means solid. It'll stay in the solid form when put in water. Okay, hydroxides, OH minus, are generally insoluble, except if they contain alkali metals or the barium ion. So again, like if I had sodium hydroxide, that's soluble, or potassium hydroxide, soluble, or lithium hydroxide. Those are all, if you notice, these are all group 1, so those are all alkali. So I could list these as soluble, soluble, soluble. Okay, also barium hydroxide, it says, is a soluble, it falls under the soluble exception. Okay, sorry, BaOH2. However, if I have FeOH3, that's iron 3 hydroxide. Iron is not one of the exceptions, so this hydroxide would be insoluble or solid. So this list of rules is not all of the solubility rules. Okay, it's just a compilation of common ones. So it won't cover every chemical. Okay, but this is just the table of observations that were made. And actually, had we been in class, you guys would have gone through a big matrix and we do what's called a solubility matrix. And you guys basically do precipitation reactions for like 50 or 60 different reactions. And then you generate a list of these rules on your own. So instead of using the ones from your book, you can refer to the ones that you've observed. And so it's kind of a fun lab where we just do a matrix of little drops. So instead of doing beakers of solution, we just do a few drops of one solution with a few drops of another, and you decide whether a precipitate forms or not. So let me go through a couple practice problems involving this, and then we'll get you ready for your test. I'll probably have a little assignment that goes with this lecture, and then we'll have a test at the end of the week. So, okay, I have pulled up here a little worksheet. Okay, and this will be similar to the types of problems that are given to you guys on your assignment. So it says, name or give the chemical formula for each of the following compounds. State whether they are soluble or insoluble in solution. Use solubility rules. Okay, so let me copy and paste this. And I'll just get the first 10. So, okay. So what you got to do is you got to look at the cation and anion. Cation and anion. And you can give it its name, and then you can look it up on the solubility table. So let's try some of these. Okay, and let me actually get my solubility table set next to it. Go. Let's move it out of here. Nope. Put it over here. There we go. So we can refer to it. Okay, so first of all, NH4 plus, that's called ammonium. And then C2H3O2 is called acetate. Okay, so ammonium acetate, you have to either find NH4 or C2H3O2 on here. So I can see right off the bat, I've got the ammonium ion, and since NH4 plus shows up in the soluble list with no insoluble exceptions, then I would say that this one is soluble. So I could just denote that as AQ. Okay, the next one, barium hydroxide. We talked about barium hydroxide. Barium hydroxide falls down here. Hydroxides are typically insoluble, but barium falls under a soluble exception. So let me get that up here. I'm just going to start writing AQ for soluble. Okay, and I can write this in barium hydroxide. Okay, iron 2 carbonate. Iron is Fe2 plus, and carbonate, you look up, is CO3 2 minus. So iron carbonate would be FeCO3, right? Just 1 to 1. And you go look up iron carbonate. Well, carbonates are generally insoluble, except when they contain alkali metals or the ammonium ion. So iron, we said, is not an alkali metal. So this one would be insoluble. All right, right, S. Okay, sodium hydroxide. Sodium hydroxide. There's our exception. Sodium is an alkali metal. Remember, the alkali metals are sodium, lithium, potassium, rubidium. Let's see, which one am I forgetting? Cesium. These are all in the first column of the periodic table. So any of those partnered with hydroxide is soluble, so AQ. And that's called sodium hydroxide. Okay, rubidium nitrate. Rubidium nitrate. Now, we've got a double thing going on for us here, right? So rubidium shows up here, and nitrate shows up in the soluble. There's no exceptions, so both of those are highly soluble. So I would write AQ for rubidium nitrate. Okay, cesium sulfate. cesium, we said was CS plus and sulfate. You look up SO4 2 minus. Well, cesium sulfate would be CS 2 SO4. Okay, and cesium sulfate, you go look, well, cesium is an alkali metal and there are no exceptions. So that one would be soluble. Or if you found sulfate, okay, and let's see if sulfate shows up here. Yeah, sulfates are also generally soluble. And the exceptions would be silver sulfate, calcium sulfate, strontium sulfate, barium sulfate, mercury 1 sulfate, or sorry, yeah, that's mercury, mercury 1 sulfate, and lead 2 sulfate. Those would all be insoluble. Okay, let's do a couple more. Magnesium sulfate. Okay, sulfates are generally, they're at the top of the list. They're soluble. Magnesium's not an exception. So this would be AQ. Zinc chloride. Okay, hopefully you guys are starting to get the hang of this. You go find zinc or chlorine. Well, okay, here's something that happens. I can't find zinc on this list. I look and I look, there's no zinc. But I can find chloride. And chloride is soluble except for these three versions of it, right? So silver, mercury, or lead. So since zinc is not one of the exceptions, soluble. Zinc hydroxide. Okay, zinc Zn2 plus. Hydroxide is OH minus. So this would be ZnOH2. And I go look, hydroxides, okay, unless they're partnered with alkali metals or barium, they are insoluble. So insoluble means they would form that solid precipitate. And another one, zinc phosphate. So zinc phosphate, I go find PO4. There's PO4. PO4 is insoluble except for alkali metals and ammonium ions partnered with it. So since zinc is not one of those, then this would also be insoluble. And not to confuse you, S doesn't stand for soluble, S stands for solid. Okay, so that's that. Now, when you're mixing solutions and you're trying to identify a precipitate, you need to do one more step. You kind of have to figure out what the potential products would be. So let me copy and paste some things so that we've got all this. Let's see if I go into here. Let's just do some precipitation writing. We won't do all of these because this could take quite a while. But let's just get a few of them. Yeah, and let me get my solubility chart. All right. So the way this works, imagine you had two beakers. Let's start with this one. You have a beaker of silver nitrate and potassium bromide, and you put them together and you observe, or you try to observe, if there's a precipitate. Well, what are your two potential products? Well, let's write this out. You've got potassium ions and bromide ions. You've got silver ions and nitrate ions. Okay, those can do our double replacement. They can switch partners. So if I switch these up, potassium nitrate and silver bromide, and these are nice because they're all 1-to-1 ratios, right? Because of the +1 and -1 charge. And so out of those two potential products, let's just list which one would be the precipitate, if there's a precipitate. So in this case, potassium nitrate, I know potassium and nitrate, when they combine, that all falls in the soluble category, so AQ. And silver bromide, bromide is generally soluble except for when it's with silver, that makes it insoluble. So in this case, there's my solid precipitate. Okay, now we could do, let's see if I can pick another one. One that I know will work out nicely. Let's try this one. This, I'll do it in a different color. What happens if you partner aluminum nitrate with sodium carbonate? Okay, so aluminum, Al3 plus, NO3 minus. Okay, that's aluminum and nitrate. And sodium is Na plus, and carbonate is CO3 2 minus. Okay, so those are the individual ions. So do your double switcheroo. Sodium could partner up with nitrate, and that's a one plus one and a minus one. So sodium nitrate. Or aluminum could partner up with carbonate. Now that's a 3 plus and a 2 minus. So I'd get Al2 CO3 3. Okay. Now looking at solubility rules, I can look up sodium nitrate. Okay, so sodium nitrate falls under the soluble AQ. And aluminum carbonate, so I go find carbonates. Carbonates are insoluble and definitely not an alkali, definitely not ammonium. So this one turns out to be the solid precipitate. I was actually trying to go for one that forms no precipitate. Okay, I see one. Okay, so let's do one more. I'll do this one in blue. What happens if you put ammonium hydroxide with barium Ba2 plus and chloride? Okay, so we're going for this box. What happens when you mix those two chemicals together? Well, barium can partner with hydroxide, BaOH2, or ammonium could partner with chloride. And those are plus one and minus one. Okay. Now in this case, and we've talked about, I think, all of these species, barium hydroxide is an exception, a soluble exception to the hydroxide rule. So this one is aqueous. And ammonium chloride, well, ammonium and chloride fall under the soluble compounds. So this would be aqueous as well. So in this case, there would be no precipitate. So this would be a very boring reaction if you did this with beakers or droppers. You dump the two together and nothing would happen. You wouldn't see any color change, you wouldn't see any solid. Okay? And we should try writing out a couple of these, but I just want you guys to know a precipitate doesn't always happen. It depends on the solubility of your products. Okay? So, okay, let me try. I'm going to do two more word problems and then you guys can try the assignment. Let's say, let me just pick one. Let's pick a metal we haven't really worked with yet. Let's do calcium. I'm going to write them out. Calcium chloride reacts with sodium carbonate. And I should say solutions of. Okay. Solutions of calcium chloride reacts with sodium carbonate. So what happens? So if I've got calcium chloride, calcium I look up, chloride I look up. So I got to write calcium chloride's formula. That would be CaCl2. And since it's a solution, I write aqueous. We could confirm also, hey, really quick. Go erase these. So chlorine is only insoluble if it's with silver, mercury, or lead, while calcium is not silver, mercury, or lead, so it's going to be soluble. Plus sodium carbonate. Sodium's always soluble. So sodium Na plus, carbonate CO3 2 minus. It's Na2CO3. Soluble. Okay, you do your double replacement reaction. So you're going to partner up sodium with the other anion. So that's NaCl. Okay, and this one, hey, I'm hopeful that you know table salt, sodium chloride is soluble in water. Okay, also all sodium salts are soluble, so AQ. Plus, you need to partner up calcium with carbonate, and that's a 1-to-1 ratio. And then you need to determine, is it soluble or insoluble? Well, in this case, there's carbonate, and it's partnered with calcium, which is an alkaline earth metal, not an alkali metal. So this one turns out to fall into the insoluble category. So I put solid. So this is known as our precipitate. Okay, based on our solubility rules. And the only thing left to do is to balance the equation. So in this case, let's see, I have 2 sodiums on both sides, so I throw a 2 there. I have 2 chlorides on both sides. I think I'm balanced now. So this would be my entire chemical reaction that's occurred in that beaker. Okay, so really what's happening is the calcium and the carbonate are finding each other and forming a white solid. In this case, calcium carbonate is known as chalk. Okay, so what we use as chalk, and what's common and probably found in a lot of seashells, this calcium carbonate is just a white solid that's not soluble in water. Okay, we can do one more. Let's see. I'll try one with some phosphates. So how about, oops, and I want to write it out. Sodium phosphate added to let's see, potassium. Let's see, potassium chlorate. What happens? Okay, so sodium phosphate, PO4 3 minus. Balance the charge, Na3PO4. All sodium salts are soluble, so aqueous. It's added to potassium, K plus, chlorate, ClO, what do I got? ClO3 minus. Oops. All alkali metals, all alkali metals are soluble, so AQ goes to form. Do your double displacement. I get potassium phosphate. That would be, we're going to determine in just a second. And then the other one, I'd have sodium chlorate. Well, we already said all sodium salts are soluble. And then we also looked at potassium. Anything containing potassium is always soluble also. So in this case, this one's a pretty boring reaction. Oh, I haven't balanced it yet, but there is no precipitation because everything's soluble throughout. The double replacement reaction looks like it would balance with probably let's see, we need a 3 here and a 3 here. Okay, and so I end up with 3 sodiums, 3 potassiums, and 3 chlorates on both sides. Okay, so there's your little intro to solubility rules. I know it's fast. It's a lot more enjoyable when we're in class, and hopefully we get an opportunity to do some experimentation. I'm excited to be back. I know we probably won't be back for first semester, but I'm going to try my hardest once we are back to do some of these important labs with you guys and those of you who are interested. So thanks for bearing with me. Give this assignment a shot. It's just going to be determining what's soluble and what's not soluble, and then writing out some precipitation reactions. So you're going to do it on a piece of paper and then submit it via picture. So, all right, good luck.